In this lecture, we're going to begin chapter 3, which is going to teach us how to evaluate properties so we can expand the types of problems we solve using the first law of thermodynamics. So at first, we're going to look at phases in pure substances. A phase refers to a quantity of matter that is homogeneous throughout in both chemical composition and physical structure. Homogeneity in a structure means that the matter is all solid or all liquid or all vapor. For example, air is a gas phase containing a mixture of different gases. Water with ice cubes contains two phases of water, both solid and liquid. And vinegar and oil salad dressing is two different liquid phases. A pure substance is uniform and invariable in chemical composition. Pure substances can exist in more than one phase, but the chemical composition must be the same. For example, our water and our ice, the chemical composition is the same. We're going to recall that the state of a closed system at equilibrium is described by the values of its thermodynamic properties. A state can uniquely be determined by its independent properties. Typically, these include temperature and pressure, but that's not always true. So we're going to look at now how to fix a state. So the state principle is a guide to determine the number of independent properties that are required to fix a system's state. Systems of commonly encountered substances are called simple compressible systems. All of the systems we're going to deal with in this class can be considered simple compressible systems. The intensive state of a simple compressible system is described by its intensive properties. For simple compressible systems, you require only any two independent intensive properties, the key point here being independent. So any two independent intensive properties can determine the state and all other intensive properties. And that's referred to as the state principle for simple compressible systems. So for example, you can use temperature and specific volume. You can use, if you select temperature and specific volume as your two independent intensive properties, then your pressure is a function of your temperature and your specific volume, and your internal energy is a function of your temperature and specific volume. Another common set to use is pressure and specific volume, in which your temperature is now a function of your pressure and specific volume, and your internal energy would be a function of your pressure and specific volume and not your temperature. The reason that temperature and pressure are not listed on the set is temperature and pressure are not always independent of each other. We're going to learn when they are and when they aren't. So the first thing we have is our PVT relationship. Your pressure, specific volume, and temperature are related to each other by this three-dimensional map of a substance. What this shows is where you're solid, where you're liquid, where you're a mixture, gives you all the information about your substance. This graph is called a PVT surface, and for pure simple compressible systems, pressure can be determined as a function of temperature and specific volume, or pressure can be a function of temperature can be a function of pressure and specific volume. A single phase region, so if you're either liquid, solid, or vapor, your state can be fixed by any two of the properties. So if you are liquid, if you are vapor, or if you are solid, you can fix your state using temperature, pressure, specific volume. All of them are independent. All you need are two to be able to fix your state. So for example, if I'm over here, I can use pressure and temperature. If I'm over here, I can use pressure and temperature. If I'm over here, I can use pressure and temperature. If I'm down here, or if I'm in here, I cannot. So if you have a single phase region, temperature, pressure, and specific volume are all independent. The difficulty comes when we are in a two-phase region. They're between single-phase regions, or when phase transformations are occurring. Those are, we have mixtures of liquid and vapor, solid and vapor, even solids and liquids. Temperature and pressure are not independent in a two-phase region, so you cannot fix your state by using temperature and pressure alone. You can fix your state if you use your temperature and specific volume or your pressure and specific volume, but you cannot use pressure and temperature alone, because in a two-phase region, they are fixed. They do not change. They are not independent. You can actually have three phases that exist in equilibrium. These are along a triple line. The dome-shaped region that comprises a two-phase liquid vapor states is called your vapor dome. We're going to be looking at that a lot. A state at which the phase begins or ends is called a saturation state. The lines that border the vapor dome are your saturated liquid and your saturated vapor dome, because you're going from liquid to vapor. On your left, you have saturated liquid. On your right, you have saturated vapor. At the top of the dome, these lines meet and you're at your critical point. The critical point is the maximum temperature at which liquid and vapor phases can coexist in equilibrium. If you are above your critical point, you cannot have a two-phase mixture. You go directly from liquid to vapor instantaneously. The pressure at the critical point is the critical pressure. So even though we have a nice three-dimensional surface that kind of explains everything that's going on with all of our substances that we're going to consider in this class, it's typically easier to look at projections of the PVT surface and only look at a 2D representation. So we have projections of the PVT surface. If we look at the pressure temperature plane, that results in what's typically called a phase diagram. So here we have a phase diagram. The two-phase regions in our domes become lines. So these lines are actually, these lines are actually two-phase regions at which there are two-phase regions where phase change occurs. The pressure along these lines is called your saturation pressure, and the temperature is called your saturation temperature. The two-phase regions, pressure and temperature, are not independent. So for example, if I have a point over here on my liquid vapor line, this is my saturated temperature, and this is my saturated pressure. And since I'm looking at a point, my saturated pressure fixes my saturated temperature. If I was to move down to a new point, I now have a new saturated pressure, but I also have a new saturated temperature. If I was to keep my saturated pressure fixed, but I was to increase my temperature, I am no longer at my saturated temperature. I am no longer in my phase change region. So again, in a two-phase region, pressure and temperature are not independent. I cannot stress how important this is. We don't actually use phase diagrams much in this course. However, I do think they help to really illustrate the point that pressure and temperature are fixed. They are not independent when you are in a two-phase region. Our triple line becomes a triple point. That triple point for water, in this case, is right here. The triple point is where all three phases can coexist simultaneously. Next, we have our PV diagram. Our PV diagram is a projection of our PTV surface on the PV plane. So it's a graph of pressure versus specific volume. We use our PV diagrams and our TV diagrams, fairly common in this course. And what's to note is the shape of the lines of constant temperature that occur. For example, this is a line of constant temperature. Also notice that if we are, here is our liquid vapor dome, and if we are inside our liquid vapor dome, our pressure and temperature both become horizontal and no longer change. The second type of graph that we typically use a lot in this course is a TV diagram, which is our temperature volume diagram. It's the projection on the TV plane. Again, temperature is constant across the liquid vapor dome, as is pressure. The biggest difference between a PV and a TV diagram are the shapes of our lines of constant pressure or lines of constant temperature. So on the PV diagram, our lines of constant temperature they decrease from left to right, whereas on our TV diagram, our lines of constant pressure increase from left to right. So let's take a closer look at this. We're gonna investigate phase change a little more in depth. So we're going to consider a closed system that has a unit mass. It's either 1 kilogram or 1 pound of water at 20 degrees or 68 degrees Fahrenheit, and it's in a piston cylinder. So I have my piston cylinder. I have liquid water. And this is state 1. And at some point, my piston is going to expand to state 2. And all of this is occurring at constant pressure. So the first thing I'm going to do is I'm going to draw my liquid vapor dome. And I'm going to draw a line of constant pressure. We're going to say that this pressure is equal to 101.104 bar. So put a few points on here. Here at point 1, our process goes like this. We're increasing our temperature and volume as our liquid water expands into vapor water. We're going to have a point F. We're going to have a point G. I'm taking a point F. And finally, at the end, somewhere up here, we're going to have a point 2. So state 1 is compressed liquid. Our temperature is less than the saturation temperature. So if I was to draw some lines over here, this is Tsat. Here's T1. So our temperature at state 1 is less than our saturation temperature. So therefore, we are in the compressed liquid zone. As we add heat at constant pressure, the temperature increases, and while the specific volume remains relatively constant, until we reach state F. State F is our saturated liquid state at our specified pressure. So we've reached the point where we have saturated liquid. That is point F, and we're now at our saturated temperature. I hope it doesn't come as a surprise that for water, our saturated pressure, for water at standard atmospheric pressure, say 14.7 psi, our saturation temperature is 100 degrees Celsius. Basically, we're at our boiling temperature. As we continue to heat, we're slowly moving across our liquid vapor dome, and we are slowly boiling more and more of our water. We're turning our water from a liquid into our gas until eventually we hit our saturated vapor phase. So once we reach saturated liquid, as we're adding heat, we're resulting in the formation of a 2-phase liquid vapor mixture, where our liquid phase is approximated as a saturated liquid and our vapor phase is approximated as a saturated vapor. We keep heating until we reach point G, where point G is our saturated vapor state. Once we reach saturated vapor, we then go on into the superheated vapor phase. But inside of the two-phase liquid vapor mixture region, we had to figure out, well, where are we along that line? How can I figure out my properties? What's really going on? What we know is that, so what we're going to do is we're going to define a parameter called our quality. And our quality is our mass of our vapor divided by the mass of the liquid plus the mass of the vapor. So it ranges from 0 to 1, where if x equals 0, it's saturated liquid, and x equals 1 is saturated vapor. Should make sense if I scroll back up to my picture. At point F, I have all saturated liquid, so there is no mass of vapor, so x is equal to 0. As we go along this line, we are slowly approaching everything being vapor, at which point our quality is then equal to 1. Again, after we reach our saturated vapor state, additional heating increases both the temperature and specific volume until we would reach our point 2, and point 2 is a superheated vapor. If we happen to be above the critical point, again, no phase change occurs. For example, there's no vaporization, so there's no liquid to vapor there's no two-phase mixture. So all of our phase changes occur instantaneously. If you heat it, you instantly go from liquid to vapor. And that's it for this video. In our next video, we are going to look at how we begin to retrieve our thermodynamic properties, and the answer to that is going to be using all of the tables that are in the appendices.